Hi everyone, my name is Aleksey Savateyev. I'm a global black belt focusing on advanced RAG design patterns. Today, I'm going to present to you a new innovative design pattern called OmniRAG, which we think is the right way to do Retrieval Augmented Generation with Azure Cosmos DB. Let's start with basic RAG first. You're probably very familiar with this picture. You take the data, you vectorize it, generate embeddings, store them in the vector store, and then when the question or the query comes in from the user at runtime, you vectorize that prompt and compare it using your vector store matching algorithm or cosine similarity against all the embeddings that you've stored in the vector store. And as the results from the vector store come back, you put them into the context in the prompt and you generate the conclusion using your large language model. And then you return that response to the user and collect the feedback. Now, there are problems with this pattern, and I'm going to showcase them based on the Cosmic Works dataset, which is similar to Adventure Works you're probably familiar with from the relational world. Let's say the user asked a question against this dataset in a conversational bot. How many bikes of each type do you have in your shop? And believe it or not, there's many different types of bikes there because this is a very large e-commerce data store um, for bikes, equipment. It has orders, customers, information, and so on. So the bot could respond something like this. There are two bikes, one mountain bike and one road bike. Obviously, that's wrong because there's way more equipment there than just two products. And the reason this is happening is because there's just too few records provided by the vector store in the results, and therefore this is all that AI gets. And of course, there are no aggregates provided. It doesn't even know the total number of bikes of each category. Now, another question could be, what is the total order amount for the road bikes with white frame? This does require a little bit of aggregation, but again, because of aggregates are not included in the vector store, and we're not executing any sort of queries against the database itself, therefore, we will not have this information. Bot response, the records provided don't contain this information. And the user might believe that, but obviously that's wrong. Another question could be, how much was my last transaction? And this is the worst situation of them all because the bot could authoritatively respond that looks like your last purchase order of $100 was made a year ago. And that is probably going to be missing the right answer by the mile because simply there's no sorting going on. There's no verification with the time going on. It's just based on cosine similarity in most cases, and therefore the result is wrong and misleading. Basic RAG is never enough. I'll go as far as saying this. There's few summaries of the problems that we've seen from real-world example shown on this slide. It only yields portion of the source data without any aggregates or projections, and that leads to lower accuracy of the entire AI solution. It motivates you as a developer to use the entire available model context window for possibly something that is completely irrelevant to the question that is being answered. And that leads to higher cost of inferencing because you're trying to use all the tokens available to you, and yet you're missing it because vector store results just don't contain the answer. It requires generating embeddings on the entire dataset, and that's simply not feasible. Some of our customers store petabytes of data in Cosmos DB or some other operational databases, and therefore it's just impossible to generate embeddings for all of them. Believe it or not, embeddings are actually larger than the average record stored in those databases. It also requires a pre-population of semantic index if you're using one. Let's say if you're using something like Azure AI Search, and you could be utilizing features such as fast search or column level statistics. This requires you to pre-populate them by guessing what the questions that the user will be asking. And you're going to miss this because there's a human on the other end. They can come up with any kind of questions that you never predicted. Again, it leads to lower accuracy and higher cost for the search engine now. So we believe OmniRAG pattern is going to solve most of these issues, if not all. In its simplest form, it can be represented in this diagram. You do have now multiple stores, not just one. Please notice this triple dot here between graph and the database. Graph is something that we add for additional accuracy, and I'm going to talk about it later, why we need that. But there could be other stores. There could be a regional database with the source data. There could be a vector store. There could be some sort of REST API for your line of business application. There could be a file system, data lake, data warehouse, whatever. You can actually utilize all of the stores in this pattern because it does give you data virtualization capability along with the RAG process. Also, its necessary component is intent detection. Since you have multiple stores, you can simply move or rather convey all your queries to the vector store and hope that it provides relevant results. You have to choose what the store is going to be that you need to serve the context from. Therefore, intent detection is important. How we do it, we give the schemas of all the stores that we have, ontologies from the graph, to the AI, and we give the original question, and AI determines what the intent is. And then once intent is detected, we route the appropriate query to the corresponding store. How do we get the query? Again, using the schemas and ontologies and using the natural language question, we generate that query in the respective query language for a particular store. Once we collect all the results from the stores, we put them into the prompt and convey them to LLM or SLM that we use. And as the response gets generated, we forward it to the user, just like in basic RAG. What's important here is that that feedback is more important in this pattern than in basic RAG. The feedback that we collect from the user, we also analyze and we feed whatever we get from that feedback to the intent detection portion so that we can adjust the golden data set of questions that we use for that intent detection based on the user feedback. So why knowledge graph? Knowledge graph is better at handling complex and multi-hop queries. As a result, it actually provides more complete and contextually rich answers to very complex questions that users might ask. It also provides the grounding source and chain of thought so that you avoid hallucinations, you provide higher traceability and audit capabilities for your process. So it goes into implementing explainable AI principle. Now, it is particularly effective for tasks that require reasoning across many documents and stores. That's what's called global search. Essentially, it gives you the ability to combine multiple, not only documents, but stores, repositories of various data that you have across your data estate. And that allows exploring adjacent topics, answering nuanced questions that actually need some follow-up information from some other stores, and so on. And the bonus feature, it saves some AI costs. I'll demonstrate that in my demo. So now, core tenets of OmniRAG, just to summarize, it is omnisource, as the name suggests. It gives you and utilizes actually knowledge graph capability, and it also gives you the intent detection capability and actually requires it, in fact. It also requires and provides runtime natural language to query conversion. And session analytics is important because, again, it feeds back its detection logic that otherwise would eventually become inaccurate. But with session analytics and that feedback loop, it becomes more and more accurate over time. Now, quick comparison between basic RAG and OmniRAG. And I have GraphRAG name here, but I'll mention GraphRAG in the context of OmniRAG specifically only. Now, with basic RAG, you only have vector. With OmniRAG, you have graph, vector, database, line of business applications, file systems, whatever sources of data you have. OmniRAG includes and requires intent detection. In basic RAG, you don't need intent detection. You have just one store, and therefore you also don't need the conversion logic as well from natural language to query. In terms of graph generation, basic RAG allows you to generate the embeddings in a very generic way, and therefore there is no logic required from you. You just need to find an appropriate vector store for your embeddings. In OmniRAG, there is a bit of logic that needs to be created if you don't yet have the graph data, if you need to actually construct a graph out of structured or unstructured data. But there is a way to actually generate the graph with the graph RAG accelerator, and I'm going to show you how you do that later. Also, OmniRAG provides you global search. Basic RAG does not. OmniRAG is scalable because, again, it doesn't require you to move the data around, generate embeddings on the entire corpus of data. You can keep the data wherever it is and only generate embeddings on the on necessary fields. For example, rich text fields in your data. You might want to generate embeddings and store them in a vector store. So how do you generate the graph? First mechanism is data wrangling. That's what we typically use with customers because they typically come to us without structured data. Well, sometimes even without structured data, but definitely without graph data. So we create a structured data out of unstructured data that they might have with something like Azure AI Document Intelligence. It essentially does the entity extraction and named entity recognition from their data. And then we create triples, subject, predicate, object, from this well-known structured data. But there's another mechanism using GraphRag, as I mentioned. It has indexing API that allows you to index your unstructured data. In that process, it generates a bunch of GraphML files. You can take these GraphML files, convert them using utility called graph2ttl. That's the script that we include in the repo that I'm going to reference later. And you convert it to turtle format, and turtle is recognizable by any RDF triple store. You load it into that store, and you do the inference in that triple store. By the way, GraphRag Accelerator also comes with inferencing option and does allow you to traverse the graph, but it's not scalable, it's not fast. I would not recommend to use it. I would recommend to use the repo that we're actually going to reference here in this presentation. And that repo is here. It's called CosmosAIGraph. It's first OmniRAG implementation. By the way, we have others. AIGraph for PG, for example, is yet another one for Postgres database. And CosmosAIGraph is our hero implementation. It is located at aka.ms/CIAG. You might want to navigate to that repo and observe what's in there. What is providing is essentially the reference implementation for OmniRAG with knowledge graph, vector database, and raw database. We use Cosmos DB for raw database. It provides a knowledge graph construction from structured data that could be in Azure Cosmos DB or a TTL file. It also provides the intent detection mechanism. We call it strategy builder, powered by built-in keyword scan or AI. And it also provides scalable indexed RDF triple store, which we use Apache Jena for. And it is in memory, and it uses persistent source such as Azure Cosmos DB for its source of the data. And it also provides natural language to graph query generator, and as well as SQL generator powered by AI and the optional feedback loop. Quick deployment architecture of CosmosAIGraph before I go into the demo. It has two microservices, Graph and Web, hosted in Azure Container Apps. They're deployed through Bicep script from the images, Docker images that are stored in Azure Container Registry. And again, as the Graph microservice that uses Apache Jena as its triple store instantiates, it loads the data from Cosmos DB. It also stores the session, all the questions and responses in Cosmos DB. It also uses Cosmos DB as a vector store and also the feedback store. And of course, we use Azure OpenAI for GPT-4o model and text embedding Ada 002 model. And the web service simply provides RESTful API and HTTP-based web UI. So instead of walking you through this diagram, I'm just going to show you a quick demo of how this looks like from the UI perspective. So when you load something like CosmosAIGraph in Azure Container Apps, it will show you the web UI here. Let me walk you through this quick demo here. Before I show you the um, uh, well, let's start with this actually. Let's execute a first Sparkle query here. As it executes, you will see that there is JSON based output. It gives you quick stats on what transpired, and it gives you some responses in JSON. So what we're asking here is the dependencies of Flask library, and it gives us few dependencies here listed: Ginger2, SGIRF, Click, and so on. And we could also visualize this graph that we have by providing the name of the library and the depth level. Why libraries, by the way? This is essentially a very simple to understand data set of PyPI repository of Python libraries. Essentially, library has developers, it's used by other libraries, kind of a natural feed for the graph data set. So as we go into a particular library and with depth level 3, that means dependencies of Flask library, their dependencies and their dependencies, so 3 levels deep. We will see much larger data set returned here in JSON, and some visualization as well. We have D3.js visualization here for the graph, and as you can see, it's pretty simple graph. As we go into much deeper level, let's say 6 degrees of separation here, it takes a little bit longer, and obviously this is much larger data set returned and much larger visualization as well. So that's just to show you what the original data looks like, because this is graph, right? I mean, it doesn't come from the graph. Originally, it comes from JSON documents that we store in the persistent store. So here's our beloved Azure database extension to Visual Studio Code, and we have Azure Cosmos DB here with CIG account, and under that account we have CIG database and 4 collections. Only one of them, libraries collection, is actually representing the business domain data, essentially in this case libraries data set. The others are service collections that we use for configuration, conversations, that means the session history, and feedback. And in the libraries collection, that's what I wanted to show you, we have a lot of documents, tens of thousands of JSON corresponding to each Python library. And let's say if we look at one of them, it has some classifiers, description, keywords, requirements, and it has dependency IDs. That's what we use in our simple data wrangling code to figure out what this library depends on. And that's how we build the graph: subject, predicate, object. This library depends on let's say black, and that would be the triple. This library, which is called accelerate, depends on black. That's one triple, and obviously each important attribute would be another triple, like keywords or license types and the ID of this library, and so on. So switching back to this, let's do something more interesting. Generate Sparkle. We can actually have some suggestions here by double clicking. If we click this button, it will generate perfectly working Sparkle query for us. So we don't have to construct that query by hand. We can simply ask a question like this: what are the dependencies of Flask library? And it will give us perfectly working Sparkle query, because we have the ontology, we have the schema provided, and we have the original question provided to AI. And AI, as you can see, will generate this query for us. We can execute it now. If we execute it, we get the same exact result as we were getting before. By the way, see how fast it is. It actually only took 5 milliseconds to provide this data set out of the graph library, because it's in memory. It's super fast, and it's indexed. Now, if we go to conversational AI, let's do something even more interesting here. Let's do this. Look up record Flask and see what it does. As you can see, the strategy detected here was database. What this means is that it didn't even go to AI. It didn't even go to the graph. It actually directly queried Azure Cosmos DB for the Flask library record, and it returned the description from that JSON field for library Flask. Zero tokens spent. That's the cheapest and fastest way to actually get that data. Let's do something more interesting here. Again, you can double click and get some additional suggestions here in our UI. But what we're suggesting here is the question, what are the dependencies of the Flask library? Again, just like the question we asked before, for uh, for familiarity's sake, we'll execute that question as well and see what happens. The strategy detected here was a graph. Why? Because we have the keyword dependencies that we recognize. We also have the word Flask, which is the name of the library. So we construct the query on the graph that returns us perfectly constructed JSON response with all the dependencies of Flask library. We don't spend any tokens on AI here at all. We don't go to the database. We get this information from the graph in memory super fast. And let's do something more interesting. What kind of libraries are most popular? And execute that one. Just to demonstrate you that actually we do have other mechanisms to serve this data. So there's mechanisms that allow you to, for example, query the vector store and the graph and the database, maybe even at the same time, in fact, depending on the rules that you provide. So in this particular case, we use graph first to consult with it, and then vector. Why vector? Because ultimately it's the vector store that will determine, by using similarity search, what is the most mentioned library, and that's why we needed this here. It says NumPy, Pandas, Matplotlib, TensorFlow, PyTorch, very popular libraries that are listed as very popular here. And again, you can observe all of this in the conversational JSON. You can say, what your feedback is, and that will get stored in Cosmos DB as well. All right, just to summarize, CosmosAIGraph is a reusable reference design and implementation of OmniRAG. It is not a product. It is built on the following: Azure Cosmos DB for NoSQL, because again, it provides persistent store for the data, supports one of the best mechanisms for vector search on the market called DiskKNN. We also utilize a number of RDF technologies, triples, ontologies, Sparkle queries within Apache Jena, which is our in-memory index RDF graph store. And we also utilize Python for user experience, data access layer, and orchestration. We utilize Azure OpenAI for industry-leading large language models, and semantic kernel for pluggable and extensible orchestration. It is designed as a set of microservices, again, could be hosted in Azure Container Apps or Azure Kubernetes Service, and could be deployed with the simple bicep script that we also provide. Call to action here, please go to the repo, aka.ms CIG, explore it, deploy it to your Azure subscription, try to adopt your custom data sets, convert them to the graph with the utilities provided, with the simple Python wrangling code samples that we have, and give us as much feedback as you possibly can on OmniRAG and CosmosAIGraph. Thank you very much.